Hi everyone. So today we'll start our third tutorial. So today we'll start our third tutorial. So before starting the topics in tutorial, so let me discuss briefly what we have done in tutorial 2. So in tutorial 2, we started off uh, building the concept of uniform energy ladder, where let's suppose this is the typical format of a uniform energy ladder, where each of these energy states are separated by a uniform value, energy E, 0, E, 2E, 3E, 4E, like this. Now, each state has a degeneracy value of G1, G2, G3, like this. Then for this kind of a uniform ladder system, we have shown that the partition function is Q equal to summation over all the energy levels. Let me use the summation index J to specify the energy levels. Gj into e to the power beta Ej. Okay. Now from here we have done the summation like this: 1 plus to the power beta Ej plus to the power minus beta Ej whole square, like this. And then from there we got the a closed got the form of the partition function in a closed format, which is this minus epsilon dvt. For a time being, let's suppose the value of beta is 1 by kVt. In today's lecture, actually, we will show how this beta equal to 1 by kVt is coming. But for just now being, we have considered the beta value is 1 by kVt. So now from here you calculate the probability, the population fraction basically in the ith state, that is pi equal to the power beta pi by q. Or in a more elaborated way, you can write it like this: 1 minus to the power minus beta e to the power beta. Okay, so this is the population fraction in ith state. Okay, so this is it. So this we have done in the previous tutorial class. Next thing what we have done, uh, partition function of a particle moving in 1D container. Okay, so we know that from quantum mechanics, right? If a particle moving in a 1D container, we know its energy level, which is given by this: En equal to n square x square n square h bar square 8m x square, but n has value 1, 2, 3, dot, dot, dot. So these are the energy state of a particle in a 1D container. And for if you know the energy states, you can basically from there we have calculated the, I mean, one can calculate a partition function, right? So for that we have we just subtract the innate energy state with its ground energy state, which gives us this kind of formula. This is, we are doing this because we want to make the ground state energy as 0. Here the ground state starts with n equal to 1, right? So that means the ground state energy will not be 0 0, right? So to make it 0, we are like subtract it of the energy level by its ground state energy level, right? So this is the format. This is the expression. So now from here I have calculated the, what is this called, the partition function, right? 1 square minus 1 beta e dn, n from 1 to infinite, right? And we, as you know, the number infinite is very high, so n should be very high than 1. For that we have approximated it 0 to infinite e to the power minus n square beta e dn. Now from there we have done all the integral, and after doing this we got the expression of qx, partition function like this: 2 pi n beta n square by half into x. X is nothing but the length of the, this is the box, multi box. This is the box is only spreads in the x direction, right? So let's suppose this is the length of the width of the box. Then this width is basically the x here. Okay. This is basically the expression of a partition function of particle that moving in a 1D box. Now from there, so this is for 1D box. Similarly, for 3D box also we have calculated. From the concept of 1D box, one can easily calculate for the 3D box. So for 3D box, what will be the expression of the partition function? So for the 3D box, we know energy will be divided into the 3 coordinates x, y, and z. So En would be En1 x E into y and v into z, right? Now from there we have sort of shown the expression of the energy partition function, that is for the all n beta epsilon x epsilon into y beta epsilon into z. Okay. So now from there, now for each of this thing, like for each of this exponential factor, we can like separately calculate the what will be the contribution of the partition function. So q is qx, qy, qz. You know, qx is nothing but this one, n1 e to the power minus beta n1 x, right? Similarly, qy would be there, qz would be there, right? So like we know the qx, similarly we know the qy, same way we can also know the qz. Now after knowing qx, qy, qz, if we substitute those into the expression of q, we will get 2 pi by n h square beta by c by 2 x y z. Now q to 2 pi n h square beta 3 by 2 x y z would be volume v. So v would be x into y into z. Right. So this is the volume of a box. X should be z, x, and y. Okay. So this is it. So now, based upon these concepts, we have done several problems. Like we have find out like the partition function of a molecule. We know the molar mass and the container of the container where that molecule is kept, and from there at different temperature you have calculated what is the translational partition function. Translational partition function simply means this is the translation, because yeah, this is the translational, because the temperature is not too high, right? So you only have the translational partition function. Okay. Now we have done this type of problem, and apart from that we have also done problem like where uh, uh, at a molecule at a particular temperature, what is the population, what is the fraction of the population at a particular temperature. that we have actually calculated by using this formula of the this formula of population fraction. So these are the basically two types of problem that we have done in the last tutorial. Now for this tutorial we will start something new. Okay, we will derive something new first. So so let's start. So we'll start from the concept of the internal energy. Okay. So we'll start from the concept of the internal energy. So so in order to find the internal energy, what I have to do, I have to first calculate the total energy of the system. Okay. So let's suppose um, let's suppose these are the energy levels E1, E2, E3, E4, E5, E6, something like that. And each energy state we have some number of particles. Let's suppose N1, N2, N3, like that. So in that case, the total energy of the system would be E equal to summation over I Ni EI. Okay. Now the fraction of the population. So so we know that the fraction of the population having energy EI would be Ni by N. This is the fraction of N having energy EI. So that would be simply Ni by N equal to e to the power beta EI by Q. So now, so if we substitute it here, then we will get E equal to summation over I N by Q e to the power beta EI by. Okay. Now from here you can simplify it more. Summation over I EI to the power beta EI. Now this thing. Okay. So we know if we do the derivative del beta of e to the power beta EI, we will simply get minus EI into e to the power beta EI, right? Now if you this same term is actually appears here also, right? The same term. So we will just substitute instead of written this term in a summation format, we would simply write this whole term in this derivative format, right? This actually makes the whole expression a bit easier. So N by Q summation over I d beta e to the power beta EI. Now from here what I can do, so N by Q I can write. So this whole thing is, there's a minus sign would be there because there's a minus sign here. Here there is a minus sign, right? So now we can write this T d beta as, so summation over e to the power beta here would be simply Q. So we can write it like minus N by N by TD beta of ln Q, right? So so this is the expression of the total energy of the system. Okay, so now as we know that if you know the total energy of the system, so now from the classical thermodynamics we can actually calculate the internal energy of the system, right? So in order to do that, so first we have to know the concept of the 0 point energy. Okay, so now we will get the internal energy from total energy. Okay, so in order to do that, you first to know the 0 point energy. That means the internal energy at temperature T equal to 0. Okay, so if you know the temperature internal energy at T equal to 0, then the internal energy U would be simply U0 plus E. Okay, where E is the total energy. Now from here U would be U0 minus N by Q delta Q delta beta. Or you can write it also like this: U equal to U0 minus N into delta ln Q by delta beta. Okay, so this is how you can evaluate the internal energy of the system. Now uh, so we have started from like the distribution of the particle, uh, in different energy levels. So from there we computed the total energy of the systems. Now we have rewrite the total energy of the system in terms of the partition function. Now from there we have got the expression of the internal energy of the system. Okay, that is U, referred as U here. Okay, so let's do some problem on this topic. Then the things will become much more clearer. Okay, so uh, let's do some problem. Okay, so assume the system has three energy levels. The energy levels are E0 equal to 0, E1 equal to del, and E2 equal to 2 delta. Now here, okay, let me write in red color. U E1 equal to 0, E2 equal to delta, and E3 equal to 2 delta. Okay. Here beta has the value 1 by kBt, and we are calculating for single number of particles. Okay, so n equal to 1. Okay, if there are more particles, then we have to like do it in a different way. But just for simplistic case, we are considering one particle system. So so now what we will do, now here the question is for this system compute E. Okay, that is the total energy. So how can you do that? So for that So for that, if you know the total energy, then from there also you can compute the internal energy if you know the 0 point energy of the system, right? So computing the total energy indirectly gives you the result for the uh, uh, internal energy. Okay. So for this kind of system, let me, the first thing that one should do always in this kind of problem is to first calculate the partition function. Okay. So partition function expression would be q equal to summation over I 0 to 0 to 2, right? Three level system. So I will be 0, 1 and 2, right? So e to the power beta ei. So it would be e to the power beta e0 plus e to the power beta e1 plus e to the power beta e2. Now e to the power beta e0 is simply 0, e0 is 0, e1 is delta, and e2 is 2 delta, right? So that means q would be e to the power 0, that means 1 plus e to the power minus beta delta plus e to the power minus beta 2 delta. Okay. So this is the expression of the partition function. Now from here, the internal energy, so the internal energy would be E equal to 1 by Q summation over I 0 to 2 psi I to the power beta EM. So that means E would be simply 1 by Q 0 e to the power 0 plus delta 1 by beta delta plus 2 delta e to the power minus 2 beta delta. Okay. So now from here, what we will do, uh, we will write delta e to the power beta delta plus 2 delta e to the power minus 2 beta delta by q. Q already we know, right? So q would be 1 plus e to the power beta delta plus 2 minus 2 beta delta. Okay, so we have calculated the total energy. Now, if you from this total energy, if in the problem it asks to calculate the internal energy, then that should be ut equal to u0 plus this original, right? Just a second. There's a Wi-Fi issue. Okay, there's a Wi-Fi issue. Okay, so anyway, so this is the expression of the internal energy of the system. Okay, the power to beta relation of the. Okay, right. So what we have done here, let me just state the problem. So we have a system of three energy level: E1 equal to 0, E2 equal to 2 delta, E2 equal to delta, E3 equal to 2 delta. For a single particle system, for this three energy level system, we have to compute the total energy. So how we have done that? We have first derive what is the partition function of the system. Thus the partition function is this, T equal to this. So we have first calculate the partition function. From there we have calculate the total energy. Sorry, this is total energy. So the total energy. So the total energy would be this. This is the total energy, where the summation of the energy with the distribution population divided by the partition function Q. So we have done all the algebra, and from that we have get the expression of the total energy. So from the total energy, if you also know the internal energy at 0 point, if you add those, you get the internal energy at that particular temperature. Okay. So this is so we do the problem number 2. Now we will do the same type of system with degeneracy. Okay. Similar three level system with degeneracy. Similarly, sorry, system has three energy levels: E0 equal to 0, E1 equal to E, E2 equal to 2. Each has G0 equal to 1, G1 equal to 2, and G2 equal to 3. Compute the internal energy or total energy E at temperature T. Okay. So now our system is slightly modified with the addition of the degeneracy associated with each energy level. Now for this type of system, first the method is similar. First we will calculate the partition function. Okay. So Q equal to, now as the degeneracy is there, so the partition function also it will be reflected like as Gi into e to the power beta E. Okay, so now Q would be G0 e to the power beta E0 plus G1 e to the power beta E1 plus G3 to the power beta E3. Now here E0 is 0, E1 is epsilon, E2 is 2 epsilon. Now here Q is, so Q would be simply G0 is what will be value? 1, right? 1 into e to the power 0 plus epsilon into 2 into to the power beta e plus 2. So next would be the second is, so this is 2 into the next is degeneracy 3, right? So 3 into e to the power beta 2e. Okay. So now q would be 1 plus 2 e to the power beta e plus 3 e to the power minus 2 beta e. Okay. This is the expression of the partition function. So now from here, we would compute the total energy the same way. So you know the expression, right? 1 by q summation over I. Now here it would be ei, sorry, gi into ei into e to the power beta e, right? Gi is also be there in the, should be there into the expression of the total energy. So E would be, so 1 by q already know, this is simply this 1 plus 2 e to the power beta e plus 3 e to the power minus 2 beta e, and g1 would be 0 into e to the power 0 plus delta into e to the power beta delta plus 2 delta e to the power 2 beta delta. Sorry, this is epsilon, right? Epsilon, yeah. Yeah. So now it's fine. So now the expression would be okay. I forgot to add the g values. Okay, g is here first. It is 2 here. Then it is 3. So 3 into 2. Okay. So now it was 2 into to the power beta e plus 3 into 2 is 6 into the power minus 2 beta e. Now in the denominator it will be 1 plus 2 to the power beta e plus 3 to the power 2 beta e. So this is the expression of the energy for this kind of system. Okay, so this problem is like the similar type of problem. The first, like the first one. So here, with the addition of this introduction of this degeneracy associated with each energy level. So for that, the expression of the partition function gets slightly modified here, which now incorporates the GI factor here, which basically encompasses the degeneracy associated with each energy level. Now from there we done the summation first. So this is the expression of the partition function after doing the summation for the 3 energy states, and then from there we have calculated the total energy E, and in the total energy expression also there should be the factor GI will be there as a factor of degeneracy, and from there we have calculated the total energy of the system. This is the expression of total energy. So this is the way. Now same way, just like previous I'm not doing, you can also calculate the, if you know the energy 0 point internal energy, you can calculate basically the energy internal energy at any temperature. Okay. Here beta is basically 1 by kBT. We basically uh, get the information like as the information of the temperature. So now, so this problem is done, problem number 2. Now we'll do the another problem, third problem. So now we'll deal with the quantum harmonic oscillator. Okay, the energy level should be different in this case. Okay, quantum harmonic oscillator. That is in 1D. We'll be dealing the 1D one. So there will be one only one indices that is along the x-axis. Okay, in the energy expression. Okay. So let me write. So in the problem itself, the energy states actually the expression of the energy state is mentioned. So quantum harmonic oscillator has energy levels n equal to n plus half h cut omega, where n starts from 0 here. Okay, in 0 at 0th energy you have energy h cut omega by 2 at 0th state. Okay, n starts from 0 in this case, 0 1 2 2. Just it's increase the number of states. So now the question is find the total energy at temperature T. Okay. Okay. So now, so yeah, basically has quantum harmonic oscillator. So its energy levels are like this. This is E0, E1, E2, E3, like this. E0 have h cut omega by 2. This has 3 by 2 h cut omega. This has 5 by 2 h cut omega. So like this, it goes on. So so each energy state basically has a separation with each other by h cut omega. Okay. So so the recipe remains the same. So first we need to calculate the partition function of the system. So for that, partition function would be q equal to n would be run from 0 to infinite e to the power beta h cut omega n plus half. Okay. So here, so now, so we can just for the sake of the calculation, you can take the e to the power beta h cut omega by half as a factor outside in the summation. So we can write it like this: q equal to e to the power beta h cut omega by 2 into n summation will be 0 to infinite e to the power beta h cut omega by n. So now q would be e to the power minus beta. Okay, so now so q would be e to the power beta h cut omega by 2. Now the summation would be n equal to 0 to infinite e to the power beta h cut omega to the power n. Now if you do the summation, you will get e to the power beta h cut omega by 2 into if you do the whole summation, so it would be like this, right? E to the power beta. So first term would be 0. N to this whole thing to the power 0 is basically 1, right? So first term you will get 1, then you will get e to the power beta h cut omega to the power 1, then e to the power beta h cut omega square. So like this, it tends towards the infinite. So So this thing can write it like x plus x square plus x cube plus this term will go on and on. So q would be simply e to the power beta h square omega by 2. If you do the summation, you know, it's 1 by 1 minus x summation of in this case the x should be the mod of x should be less than 1. Like in our case, this should be true, right? So this is basically the summation of infinite geometry series. So so now you can write it. So you can write this whole partition function in a closed format, right? This is the beauty of this problem. You can write this whole partition function expression in a closed format. Okay. Okay. So this is the expression of the partition function. Now, so as we got the partition function q as a closed format, now what we can do, we can simply use this this expression, right? Let's simply use this total energy expression as which we previously derived in terms of a derivative of the beta, right? We have to compute the ln q, and if you do the derivative with respect to beta, you get the total energy expression, right? So if you do it, uh, so we got the q expression, then from there the energy E would be minus derivative of beta into ln q, the derivative of beta equal to minus beta h squared omega by 2 minus ln of 1 by e to the power minus beta h squared omega. Okay. Okay. So this we got, right? So now okay, so uh, now we have to do the derivative. Okay. So in order to do the derivative, so E would be first will derivative, do the derivative with respect to this beta h squared omega by 2. Next, minus minus will become plus, derivative of beta with respect to this derivative of log this term with respect to beta equal to beta h squared omega by 2. So now if we do the same, energy E would be h squared omega by 2 plus h squared omega into 1 by the power beta h squared omega minus 1. Okay. Now, so this is so log of 1 plus 1 minus e to the power beta h squared omega. So first derivative, this thing will comes in the denominator. Then if you do the derivative, there should be a minus. No, it's fine. So yeah, so there should be a e to the power beta h squared omega term will also be there. So e to the power minus beta h squared omega, so minus 0. Now it's okay. So this, after doing the derivative, you get this. Now we'll further simplify it. So you can take h squared omega as common, right? H squared omega, then you get half plus we can divide e to the power beta h squared omega in the numerator and denominator, then we'll get 1 by, okay, so it would be like this. So this is this now it's perfect. Now if you multiply e to the power minus beta h cut omega both in numerator and denominator of the second term, then you will get this e to the power beta h cut omega minus 1. Okay, so this is the expression of the energy of gravity. So let me just repeat what we have done. So this problem is different. So here the energy level, so we have to evaluate the total energy of a 1D quantum harmonic oscillator. Okay. So the energy levels are already given, and we already know in a quantum harmonic oscillator what is the energy levels. This is the expression of the energy levels. So the first thing that we do, as always, the partition function. So we have calculated the we have like do the summation over the energy state n in order to find the partition function, and then from there we got this infinite geometry series. Then we know the what is the summation of the infinite geometry converging infinite geometric series, and we have got this expression in the closed format, which is basically this. And then from there, if we got the cube as a closed format, then we can simply use this formula, right? This derivative that we have derived earlier, this formula, right, in order to get the expression of the total energy. So we have done simply the same thing. So after calculating the partition function, we have substitute the q into this formula. Then in the ln cube form. Then from there we have done the derivative with respect to beta, and after doing that, we got this total energy, which is this, simply this. So this is the basically the expression of the total energy. This is a type of problem. So this is it for the quantum harmonic oscillator. Okay. Now what we'll do, like in previous all the tutorials and all the problems that we have done so far, we have considered the beta value as 1 by kBt, right? In the previous problems, beta value we have considered 1 by kBt. Okay, but we have not technically derived how this beta equal to 1 by kBt is basically coming, right? So that can be actually derived. Okay, so I will give you a very brief kind of derivation, like how this beta equal to 1 by kBt thing is coming. Okay, so okay. So after doing that, we will simply move to heat capacity and entropy. Okay, expression of the entropy. So okay. So for this problem, just separate thing. We will calculate the expression of beta, that is a Lagrange undetermined multiplier, right? That we have encountered before, right? So in order to do so, we will calculate the internal energy. So we will calculate the internal energy for an ideal gas, and then from there we will calculate the expression of the beta. So how can we do that? So for that, uh, we know the internal energy expression, right? How the internal energy is related with the total energy, that is U equal to U0 minus E plus E, and U equal to U0, E expression you already know, that is minus N by Q delta Q del beta, right? Now from here we know Q is simply V by lambda Q. Okay. Okay, so let me say, so in the previous lecture, so let's suppose uh, for an ideal gas. Okay, so for how an ideal gas basically moves. Ideal gas basically moves in a container, right? In a 3D container. In a 3D, so this is a 3D container. So it moves like a monoatomic ID as a monoatom, right? Single atom, right? So we know, like when a single atom, or in this case it will be ideal gas, is moving in a 3D container, then the partition function expression is simply this, right? Q equal to V by lambda Q. We have discussed about it, right? The lambda is basically thermal wavelength in the last tutorial, right? For lambda is, V lambda, what is lambda is simply beta by h square by 2 pi m half, right? This is the expression of thermal wavelength lambda. Now this we already know for a 3D partition function for a particle in a moving in a 3D box. Now if we substitute this partition function expression into the expression of the internal energy, then we'll get simply equal to U0 minus N by, so Q is basically V by lambda Q del beta of V by lambda Q, then from here equal to U0 minus N by lambda Q minus 3 by lambda to the power 4 del lambda del beta at a constant volume, right? Now from here we can write U minus U0 equal to 3 N by lambda by half. If you do the derivative of lambda with respect to the beta, in the lambda expression the beta is already there, so you can easily do the derivative. You do the derivative del lambda by del beta, then you get simply half of beta a square by 2 pi m means half into beta h square by 2 pi m into 1 by beta. Then from here U minus U0 would be, now here what will happen, many things will cancel out, right? So like this beta will cancel out. If you substitute the expression of the lambda here also, 3n, so this is already the expression of the lambda is here, right? 3 lambda, this is also the expression of lambda, right? And h square by 2 pi m is there also. So if you encounter all of this, lambda will cancel, beta already get cancelled, 2 pi m get cancelled, then from there you will get equal to 3 by 2 n by beta. Okay, this would be the expression you get. This is the minus of, okay, so now it's a minus of, so now u equal to u0 plus 3n by 2 beta. So we have derived the internal energy for a particle for an ideal gas. So in order to do so, we have used the concept that if a particle or an atom, monoatom, is moving in a 3D box, this translational partition function of of this sort of a system, Q is simply this V by lambda Q, or lambda is simply, you know, the thermal wavelength. And if you substitute the Q expression here, we will get this type of expression of the internal energy by U equal to U0 minus N by V by lambda Q. Now from here, if you do the derivative of V by lambda Q with respect to beta, you will get d lambda by d beta term here. And so you substitute the expression of Q in here. And after doing that, you have to do the derivative of lambda, because lambda is a function of beta, so you have to do the derivative of lambda with respect to the beta. If you've done so, then you will get this kind of term. If you do all the common term out, then from there the u minus u0 expression you will get like this, 3 by 2 n by beta. So that is, now the next thing is, so from the kinetic theory of the gases, from the kinetic theory of gases, that we have learned, right, in our previous thermodynamics course, we already studied about the kinetic theory of gases, right? So in that kinetic theory of gases, the total energy of a gas, of ideal gas in 3D would be simply energy equal to 3 by 2 nRT, right? This is the total energy of a ideal gas moves in 3D, right? The 3 by 2 factor comes because of its 3D. If it is in 1D, that factor would be simply become 1 by 2, right? But that's a different thing. So the total energy is this, you already know, right? So from kinetic theory of the gases, if we already know the expression of the total energy, if we know the expression of the total energy, then the internal energy expression would be simply U equal to U0 plus 3 by 2 nRT. Okay. So, so this is basically the expression of the total energy of the system. Okay. Now, sorry, the internal energy of the system. Okay. Uh, now having that in our hand, uh, next what you want to do, we will simply compare these two results. Okay. This is the 1, this is the 2. Now, comparing 1 and 2, we will get 3 by 2 nRT equal to 3 by 2 n beta, right? So, n is simply, here n is the number of particles, right? That means number of moles into Avogadro number. That will be the total number of particles, right? So 3 by 2 nRT by 3 by 2 n into Na by beta. Now Nn would be simply cancelled. R we know the gas constant is Boltzmann constant into Avogadro number, that you already know. So beta would be simply Na by R into T. So Na by R is simply 1 by K. So 1 by KBT. Okay. So this is how the expression of beta is basically coming. Okay. So we have basically proved it in the context of an ideal gas. Like we have first calculated the ideal gas problem. Okay. Ideal gas problem using the formulation of partition function, like how we have done in the previous problems. Now, using the kinetic theory, we have also calculate in a different way of calculating internal energy. In previous case also we calculate the internal energy, but using the partition function. Next way, we have calculated the same internal energy, but using the kinetic theory of gases. And basically we then compare the two results, and from there we get the expression of the beta, which is equal to 1 by kBT. Okay. So this is a problem. So this is a way. The next thing what we will discuss is called the heat capacity. Okay. Now this heat capacity will do further problems on this also. Okay. So heat capacity is basically very important concept of any kind of thermodynamic system actually, because uh, heat capacity basically tells you, like if you basically calculate a thermodynamic quantity at a different at some temperature of a certain material, then by using the heat capacity you can predict what is the measurement of that thermodynamic quantity of that material at a different temperature. Like using just the heat capacity you can do it. In case of material science, in the like point of view of a material scientist, this or a condensed matter physicist, anything, this heat capacity is a very important quantity, okay, in thermodynamics. So uh, so basically heat capacity is a very important quantity in thermodynamics that is used to connect to thermodynamic quantities at two different temperatures. Okay, so that's it. Now, if you know all these things, so okay, so now first is, so how can you get the expression of the thermodynamic? Uh, so there are basically two types of basically specificities there. One is at constant pressure and one is at constant volume. Okay. Cp is specific heat at constant pressure, and Cv is specific heat at constant volume. Okay. So in general, the expression of specific heat is simply dq by dt. Okay. Like the fundamental definition of heat capacity is like the amount of heat that is required by material to raise its temperature by the amount dt. Okay, so if dq is the amount of heat that is required to raise the temperature of a material by the amount dt, then their heat would be dq by dt. Now, depending upon what quantity you kept as constant, uh, Cp would be either dq by dt at constant pressure, or Cv would be dq by dt at constant volume. Okay. So now, uh, you can further simplify it actually. So, for case, so let's first do for Cv. Okay. So Cv we know from first law of thermodynamics. First law of thermodynamics. We know that dq equal to du plus dw. Dq is we know dq is du we know, and dw is pdv, right? So for this case, if the volume is constant here for the case, so dv would be 0, right? At constant volume, dv would be 0, right? So dq would be du, then dq by dt at constant volume, that is simply Cv is simply du by dt at constant volume, right? So the expression of Cv, you can write it as du by dt. Okay. Now, similar way, uh, you can do it. You can write the expression of CPDT, sorry, the expression of Cp in a different way. So for that we need the expression of the enthalpy actually. Okay, so we know the enthalpy. You already knew this term, right? Enthalpy, which is expressed as H. So we know dH is basically du plus pdv plus vdp. Now du already know, du is conditions. Okay, there is some connection issue. Okay, anyway, so dH is simply, so du expression you already know. Du is dq minus pdv, so plus uh, pdv minus pdp, so pdv is cancelled, so dH is simply dq plus vdp. So now if you do at constant pressure, so we want to calculate now the heat capacity at constant pressure, right? So at constant pressure dp is equal to 0, so dH by dt at constant p will be equal to dq by dt at constant p. This term will become 0. This is simply the Cp. Okay, and this is the Cv. Okay. The CPCV we got, right? CPCV both we have got, right? So Cp, so we can write, so that means that we can write the expression of CPCV in terms of enthalpy, or in case of a Cv, we can write it in terms of the derivative of internal energy with respect to temperature, right? So for for a gas, for ideal gas, we know ut is u0 plus 3 by 2 nRT, right? So that means ut by minus u0 is 3 by 2 nRT, right? That is the time. So for ideal gas. So that means if you if you know the delta U change in internal energy, if you change the temperature by 0 to T, so from that you can easily calculate a CV, right? In case of in case of an ideal gas. So CV we know is simply can write as a du dt at constant volume. That is simply would become 3 by 2 nr, right? T will be gone. So this is basically a fixed term. CV is basically a constant term. 3 by 2 into nr. So this is the way you can calculate the specific heat at constant volume for an ideal gas. So now, the next thing that I want to do. So the entropy, the specific concept we have now known. Now after that, we will do uh, one of the important concept in any kind of statistical mechanics or even in any branch of physics. This is a very important quantity. This is called the entropy, right? We already heard about this thing, right? Entropy. Okay. So we'll start the entropy thing. We'll also do problems on it also in the end. So the thing is, from classical thermodynamics, we know Ts equal to dq reversible by temperature, which is now this is for a only for a reversible process. This is true for reversible process. Okay, this we have like no, from classical thermodynamics, right? We like in previous courses we have already studied about these things, right? Now in constant volume, so in case of constant volume, you can write dq reversible as du, right? In constant volume, you can write dq reversible as du. Okay. So now, if you know that dq reversible is equal to du, now what you can do, you can write u equal to u0 plus e. So now you can write du equal to du0 plus de. Now we already know E is basically summation over Ni by Ei. That we have done, right? If the energy levels are 1, 2, 3, each energy level we have particles N1, N2, N3 like this. Epsilon, epsilon, epsilon 3 are the energy levels. Then the total energy of the system will be the summation over Ni into Ei, right? This thing we already learned, right? So now, so dE you can write it like this. So du is simply du is 0 is a constant value, so it simply becomes 0. So dE simply becomes Ni into dEi plus summation over Ei into dNi. Now the thing is, here what happens in this when you change the temperature or like any kind of other thermal property of the system, what happens? the energy states, the particles, so the particles basically changes its states from E1, let's suppose E2, or from E2 to E1, or E2 to E3. So basically the number of particles will change from different states to states, okay. But the states remain same, okay. States doesn't change. The value of energy in each state will remain fixed, okay. So that means the change in internal energy will be contributed from this term, right, where the change the number of particles is change in each energy state, that is defined here by dNi, that is the change in particle number in ith state. Although the energy states, that is the energy of the ith state dEi, that is remain fixed. The energy state itself doesn't change, right? It kept as its original fixed value. Okay. Only thing that changes the number of particles that in that corresponding energy level. Okay. So that means dEi is simply 0. Okay. So this whole term will become 0. Right. So du is simply become summation over I Ei T N. This is the expression of the change in the internal energy of the system. Okay. So now, as we know this, the expression of the du, now as we know the expression of du, what we can do next is to check few things. Okay. So okay. So we know the expression of the du. Now what we do, so now in the next thing we will do, so ds, so du you already know, du is related to the entropy. We know that ds equal to basically du by t, then you can write ds then 1 by t by summation over I ei dni. Now ds you can write it like, so what you can do, we can further simplify it. We can make it 1 by kbt summation over ab ei dni. So 1 by kbt, you can write it as k into beta summation over I ei dni. Now so so again ds, sorry, this is ds. So ds you can write is k into summation over I beta ei dni. So now from the from that previous to previous lecture, in the first tutorial, we have calculated the extremum of our distribution, right? So like where we have encountered that uh, Lagrange Lagrange undetermined multiplier method. Using that method, we have calculated the maximum of a distribution, which appears to be a Boltzmann distribution, right? So from that concept, we know this thing, right? Beta ei equal to delta ln w by delta ni plus alpha, right? This w is basically the configuration, right? This we have actually discussed in the tutorial 1, right? Beta is the undetermined multiplier, alpha is the the first undetermined multiplier, right? So yes, we'll substitute this beta ei here actually. So k would be simply become summation over beta ei is this delta ln w to delta ni to dni sorry, plus alpha into dni. Now from here we'll do the summation. So summation would be k is summation over I ln w delta ni into dni plus summation over k into summation over I alpha dni. Now from there ds would be summation, k would be summation over I delta ln w delta ni summation over I dni. Now here the total change in the particle, the total change of if you calculate the total number of change of the particle between each state and other state, simply the total change would become zero, right? Like two particle will go to first state, then that means the first state will get two plus two particles, then the ground state will lost two particles. So if you add all the particles, that is basically interchanging from one state to another state, that will simply gives you zero, right? Because the whole change would be zero because the number of particles itself is constant, right? So that's why this whole thing will become zero. So now that means ds would be k cancels, k would be d ln w. So ds, so s is d ln w, then s would be k ln w. This is the expression of the entropy. Now this is the expression of the entropy. So now w is the configuration. So w we know, uh, if out of n particle, if you put in one particle in compartment 1, in two particle in compartment 2, in two particle in compartment 3, and likewise, then the number of possible combination would be n factorial divided by n1 factorial, n2 factorial, n3 factorial, and likewise. This is the weightage of this configuration that we have explained. So this weightage. So uh, if we do the log ln both sides, ln w would be simply ln n factorial minus summation over I l ni factorial, right? That we have done previously, and using the Starling approximation, we have done these things actually previously. L n minus summation over I ni ln ni. So these are using Stirling approximation, right? We got this thing, right? So now this whole thing becomes like, so now if we got ln w expression, now from there itself we can calculate the entropy, right? So x would be simply k into n into ln n minus summation over I n I. Now you can rewrite this. This we are doing just for sake of faster calculation. Summation over I n I n I. Now from here itself you can write it like this. You can take the summation outside. K summation outside ni ln n minus ni ln ni. Now from here the is, you can write it like this, summation over I Ni ln Ni by n. This is a negative sign we will put, so the whole thing will become minus Nk. After doing the summation over Ni, we will get the particle. So when we are using this thing, Ni equal to n. So here, so this would become Nk. So now this Ni upon n is nothing but the population fraction, right? So this we have written it as Pi, population, population fraction in an ith energy state, right? So Pi is there. So you can write this whole thing is like this. Summation over I, Pi, ln, Pi, okay. Yeah. We are subtracting n here and we have add n here. So from that you get this step. So now we will use some algebra of log, of the properties of log. So we know that Pi is e to the power beta e minus beta ei by q. So ln ei would be simply minus beta ei minus ln q, right? So entropy would be that in that context, entropy would be minus n by k summation over I ei. Ei is a probability minus beta ei minus ln q. Okay. Now, if you do the algebra, then it will give you n by k summation over I pi beta ei plus n by k summation over I pi ln q. So now the entropy would become summation over S. So we have to just make this whole thing simpler. Ni by n into beta ei plus n into k. You can write this pi here. It will keep pi as it is. So you can actually keep this ln q outside. You just summation is only over pi is there. So now entropy, so ln would cancel. So now it will become beta is going to go outside I Ni ei. This becomes nk ln q. The probability is the summation over all the probabilities gives you basically 1, right? Summation over all the probabilities gives you 1. Now this would be k beta summation Ni ei gives you total energy E plus n by k ln q. Okay. Okay, fine. So this is basically the expression of the entropy. Okay. Now, yeah. So you can write further simplified actually. Beta is 1 by kBt, right? So you can write it E by T plus nk nq. Also you can write it in terms of internal energy, right? Ut minus u0 by T plus nk by n. This is also a way you can write it, expression of the entropy, right? So this is it. So this is how you can calculate the entropy of a system. Now the next thing is what you can do. You know, you have to use this factor is basically ut minus u0 here. Okay. So we got the expression of the entropy, okay, in a very user-friendly format. We got it. Now, now, So now here what you can do, let's suppose any system is given. We will come to the problem in few more minutes. So what we can, how we can use this expression? Okay, what is the significance? As you can see, this expression is dependent upon both the internal energy of the system or the total energy of the system, the temperature, the number of particles, and the partition function, the most important thing here. Now, the energy itself, or the change in the internal energy, that is itself is dependent onto the derivative of the logarithmic of the partition function of the system. Okay. So that means if we know the temperature, the number of particles in the partition function of a system, then we can, in thermodynamic equilibrium case, obviously, that is the basic consideration that we have to make. We can actually calculate the entropy of the system, okay, for any kind of system which are in thermodynamic equilibrium. Okay. So we will actually basically do a kind of problem. Okay. So for three-level system, three-level single particle system n equal to 1, we will derive, we will basically calculate both all these things: this internal energy, specific heat, and lastly the entropy, how the entropy behaves basically. Okay. So we'll do it. Let me just check what is the status of the recording. This recording is doing fine. So okay. Okay, so let me first write the problem. Consider an identical independent three-level system whose single particle energy levels are 0, E1, E2. So what you have first will calculate heat capacity at constant volume, that is a CV. So the first we'll calculate the CV, then afterwards, if we time permits, then we'll calculate the other things like entropy and all those things. So so what we will do, we will first write the partition function. Okay. So the partition function of this can, there is three energy levels there. 0, E and 2. Three energy states are there. So first we have to calculate the partition function of the system, which is written as Z beta summation over I 0 to 2 to the power beta EI. So Z beta would be e to the power beta into 0 plus e to the power minus beta into epsilon plus e to the power minus beta into 2e. So Z beta would be simply 1 plus e to the power beta e plus 1 plus e to the power 2 beta e. Okay. Now if you consider x as e to the power minus beta e, so the Z would be simply 1 plus x square. Okay. Now, okay. So you got Z is nothing but the partition function. So instead of writing it as Q, I'm writing it as Z. Okay. So now the internal energy or the total energy that you can easily find out, right? du or so internal energy is the total energy anything d is equal to basically minus n del del beta of ln z, right? So now ln z would be ln of 1 plus x squared. So del del beta of ln z would be simply 1 by zeta z into del del beta of z, which is 1 by z into del del beta of 1 plus x squared. X you already know is e to the power beta a, so that means it would be del del beta of ln z would be simply 1 by z del beta x plus del beta x square. So that would be simply becomes 1 by z into del beta del x would simply become 1 second. Showing internet, 1 second. Let's issue an internet. Okay. So so we are in, yeah. We're computing this, right? So del beta del z is nothing but, sorry, del beta del x. Derivative of x with respect to beta is nothing but minus epsilon to the power beta e. So that means minus epsilon naught. Similarly, del beta of x square will become 2 epsilon into x square, right? Similarly. And now if you substitute these two here, then it will become del beta of ln z would become minus epsilon x plus 2x square whole divided by the partition function z. Okay. Okay, so up to this you already all of you I guess you have understood. So here we have started from the expression of the partition function. We are mentioning it as z. So this is the total partition function. Now in order to calculate the total energy or internal energy, whatever, you need to do this thing that we have derived earlier. From the partition function, how can you calculate the total energy or the internal energy? That is basically given by this. So now first we have done the log ln z, which is given by this factor. Now if we do the derivative del beta of ln z, del beta of ln z, you got this 1 by z outside, then del beta of z, del beta of z is 1 plus x plus x square. X is nothing but e to the power minus beta e. So del x by del beta is simply epsilon to the power beta epsilon, so that is epsilon into x minus epsilon into x. Similarly, x square derivative with respect to beta will gives you minus 2 epsilon x square. Okay. So after doing all this substitution and all, del beta of ln z, you will get this expression simply minus epsilon x plus 2x square by z, the partition function again. So now, after doing all of this thing, now we will simply evaluate the CV, the specific heat at constant volume. So CV. Okay, so for CV we can computed the E, right? So we know the U first. Let me write the E or U like this. This is minus n is there, so E is minus n, so minus plus n, right? Plus n, yeah, now it's fine. So U or U will be simply n E x plus 2x square by 1 plus x plus x square. Okay, this is the expression of the internal energy or the total energy of the system. Okay, so now after having that, we can calculate the CV. Okay, CV is the specific heat at constant volume. Okay, so what is the expression of the CV? We have derived it earlier, right? So CV expression is simply like this. CV is du dt at constant volume. So du dt is basically, so now what we can do here, so here x is e to the power minus beta, right? So it's better to write this derivative terms not in terms of beta or not in terms of t. Instead we would write the derivative in terms of beta, because if you write the derivative with respect to beta, then the calculation for us become lot easier, right? And t or beta we already know it's interconnected, right? So we can write this thing like this. So du by dt, you can write it like this: d beta by dt into d of d beta u, like this. Now beta we already know 1 by kBt, that you know, right? So dB by dt simply gives you minus 1 by kt squared into du by d beta. Okay, so Cvu that sense minus kt squared by du by d beta. Okay, so that means 1 minus 1 by kt squared d beta of in epsilon x plus 2x square by 1 plus x square. That simply gives you now can take 1 by kbt square as whole common. You have to do the derivative, the whole derivative you have to do 1 by kt square. So first would be 1 plus x square of d beta of x plus 2x square plus plus or minus, just a second. So let it write inside a bracket. So now if the derivative on other side, so it will become x plus 2x square 1 plus x square whole square d beta of 1 plus x square. This is it. So now Cv would become minus 1 by kBt into d derivative of beta with respect to x. So it gives you 2 beta x plus 4 beta x square 1 plus x square. You already know, right? D beta of dx would be minus. There's a minus would be there, right? So minus. Yeah, right. So epsilon of beta. X is simply minus epsilon x, and this is 4 epsilon x square. 4 epsilon x square minus of this is becomes x square e to beta of x is minus epsilon x minus 2 epsilon x square 1 plus x by x square whole square, right? Now if we do the Cv, it gives you 1 by kBt so 1 by kBt 1 by kBt is there. Everything will go this side and that side, so this side x plus 2x square epsilon come outside, minus will become plus x plus 2x square, so this plus 2x square whole square will become anyway then 1 plus x square whole square. This term would become minus will come outside, so epsilon x plus 4 epsilon x square into 1 plus x square. So this is it. So Cv would become if you simplify it more, it would become nk beta is square plus x plus 4x square by plus x square minus x plus 2x square by 1 plus x square whole square So this is it. So now this is the expression of CV basically got here. Okay, so we got a familiar expression of the CV. Now uh, we can also calculate the expression of the entropy from here, right? Expression of the entropy, you know, we need the total energy and the logarithmic of Q, right? Total energy we already calculated, and the partition function Q or Z, whatever, is is previously like initially we have evaluated, right? So we just need to substitute those two expression here in order to get the entropy of the system. So we'll do so. So entropy would be, let me first write the expression of entropy. Entropy would be simply E by T mine plus Nk plus Nk ln Q or ln Z in this case. So okay. Okay, so there is an internet issue anyway. So so what we have calculated the expression of the entropy. So just we have to substitute the expression of total energy and log of Z. So if we do so, then we'll get S of Nk ln of 1 plus x square. Next, Nk would be outside plus beta E x plus 2x square by 1 plus x plus x square. If you do the mathematics, like ln Z and E you already know, this is the E, and ln Z you already know, ln Z also. So this is ln Z, this is ln term, yeah. So this terms comes from ln Z and this terms comes from the total energy E. So this would be the expression of the entropy of the system. Okay. So this is how you can calculate the entropy if you know the partition function. So if you know the partition function temperature, you can basically calculate entropy, total energy, capacity specifically. So that's it for today's class. Okay. Okay, so let me stop the meeting.